Okay, so today's, this one's, it's kind of interesting, and some of it's review, actually. This webinar, I'm going to go over to start with some basics on R squared CVRMSE in case you just come to these things and don't know what we're really talking about. This is about regressions, regressions of utility bills, but it could be daily data, it could be weekly data, it could even be interval data. And the whole point, I guess, or the context of what this is about is that how can you tell if your regression is good enough? How do you know? And the so people have come up with, or these organizations or entities have come up with these standards or ideas of how you can determine, is this regression reasonable, and should you use it when you're trying to estimate energy savings from, you know, doing a performance contract or some kind of energy conservation project. Okay, so we're going to go over a little bit R squared and CVRMSE. This is review for some of you, but that's okay, and we won't go too much review. And then basically some recommendations from some organizations, and then I'll explain what I did with my experiment and what I learned. It's kind of neat. Now this, what I'm going over here actually was in a paper that, you know, I said Evo never publishes me. Well, they did publish me. So it's in Evo's newsletter, and it's also an AEE publication. I didn't know they were going to do that, but they published this too. So it's in International Journal of Energy Management. This month's issue, it came out. Okay, well, let's get going. So first off, this is a regression. So all those dots represent utility bills. You know, when you're doing this M&V, you know, option C type M&V, you know, usually use about 12 bills, 12 or 24, and you do a regression, you know, versus weather, usually, depending on the meter. There could be other variables, but we're not going to go there today. And the regression really is just the best fit line through the points. And there's these statistical indicators that they're down here that would tell you, you know, is this a reasonable regression or not? So these are some of the, let's say, what people have told us, or what we've read, you know, in different documents from ASHRAE or Evo, et cetera, about what makes a regression good. So I started in this performance contracting business a long time ago, I guess in the 1990s. So I think mid to late 90s I was in. And what everybody was saying back then was you need an R squared above 0.75. And still you'll find, certainly old timers, that would include myself, who talk that way and say, yeah, you need an R squared, you know, above 0.75. Actually, I don't talk that way, but people my age do. And right. And so that's one of the things that we've been told, is that's how you can tell the regression's good. It's above 0.75, use it. ASHRAE 14 came up with this thing that the CVRMSE, which we'll talk about in a minute, you know what it is, but it should be less than 35% for energy. Now, that's not exactly what they said, but pretty much, and I'll explain what they said in more detail in a later slide. And then Evo has this where they say this, that the CVRMSE should be less than 50% of the savings fraction. Savings fraction is what percent do you expect to save from this project? So if you expect to save 20%, then your CVRMSE should be 10% or less. Okay, so that's a little harder to meet as a standard than that one. Okay, so here is a fit that's not very good, actually, but you can see as it gets warmer, they do use more, so there is a trend, but there's a lot of scatter around the fit line. You see all these points, and they're scatter. Down here, you can see the CVRMSE is 16.53. I'll talk about it in a minute again in a little more detail, but maybe I'll just repeat myself. But the CVRMSE is a measure of scatter. So it doesn't exactly, but it kind of means that the average bill is about 16.5% off from the fit line. Kind of means that. The R squared value is lower than 0.75. It's 0.4, so it's a really lousy fit. And this is a fit you would throw out. or at least according to what we hear. Now, but the CVRMSE is less than 35%. So according to that rule, it's okay. It gets funny and confusing because there's always different, things to listen to. And then, well, which one is it do I listen to? And we'll talk about that a little later. Okay, so let's talk about the R squared value. It's also called the coefficient of determination. Basically, it's what I wrote right here. It's to what extent does the independent variable, that would be cooling degree days per day, determine the variation in the dependent variable, which here is kilowatt hours per day. So to what extent does it do that? That is what it measures. The problem with the R squared value is that if you have a, let's say, less steep slope, you end up with a lower R squared value. So this graph is showing, in both cases, we have the same scatter or the same CVRMSE. You'll see that the dots are about, equally far away from the fit line, about. They have the same midpoint or average bill, and the R squareds are way different, all right? So that's a problem with R squared. So if you had, if you're in San Francisco or Hawaii where the weather's the same almost all the time, you're going to end up with a low slope, and it's going to be hard for you ever to get an R squared above 0.75. Okay, so let's look at this equation. This is how the R squared is calculated. The top is how far is the bill from the fit line. Okay, and then the bottom is how far is the bill from the average bill. All right, so if the average bill, I think I have it here, as the line flattens, the top and bottom converge. What's that mean? Actually, let's look at it this way. As the line is flat, let's assume the line is exactly flat, then these are the same. These are the same because the average bill is every point on that line because it's the same kilowatt hours every day, right? Every month, it's the same. And so how far the bill is from the average bill is also how far it is from the fit line. So the R squared would be 1 minus 1, which would mean the R squared is 0. So that's an extreme case. I mean, if the bill is the same every month, you're not going to do a fit anyway. But I'm just trying to explain the extreme case and how as the slope flattens out, the R squared goes towards 0. Okay. So let's go back and look at this again. There it is. So, right. Okay. Next. Okay, the CVRMSE, as I mentioned, was a measure of scatter. So this is what ASHRAE 14 really says. It doesn't say it should be less than 25. It says if you're using a post-retrofit savings period of, 1 to 5 years, it should be 25, less than 25. So if you're using more than 5 years, then it could be 30. Okay, and actually that's what most performance contractors are doing. So that's what that's. They also have stuff about the fractional savings uncertainty, but we're not going into that. Okay, this is the core concepts put out this year by EVO. It says that standard error of the estimate must be less than 50% of the expected savings. This is actually really confusing, but basically it is this. The CVRMSE should be less than 50% of the expected savings fraction, or in other words, if you're going to save 20%, then your CVRMSE should be less than 10%. That's basically what it's saying. Okay. So here's a problem with CVRMSE. Here we've got the same R squared on both. Notice it's really low, it's because they're flat. And yeah, the scatter is the same, okay? But one line is a lot higher than the other, and we have much different CVRMSEs. So what we're finding is that the CVRMSE is going to be much higher, or in other words, worse, if the average bill is less. Why is that? Because we're dividing by average bill. Okay, so it's how far the bill is from the fit line, and then we have average bill. So as average bill goes to 0, in other words, as it gets smaller and smaller, the CVRMSE gets higher and higher. Yeah, so let's say your average bill was 0. I mean, that means you don't have any bills, but let's just say, then you're gonna have a CVRMSE of infinity. Okay, so that's the problem with CVRMSE. So they both have problems. And so neither is really useful all the time. But we have these bodies telling us that, well, you need the CVRMSE to be this or that or the other thing. Look, these guidelines, or whatever you call them, the ASHRAE 14 and the core concepts, they're not perfect. And their recommendations aren't perfect. That's where judgment comes in. And we were having, in the last week, we've been having this pretty kind of, I guess, emotional, occasionally discussion, myself and like 4 or 5 other people about this. And I think this was the conclusion that we came up with. And actually, Christy, I don't remember your last name. I mean, I know your last name. I don't know how to say it right. I guess I won't, but Christy knows who she is. But she came up with this, and she's absolutely right. It's all about judgment. It's judgment. We have these guidelines, and we decide what to do with them. And sometimes we use them, and sometimes maybe we should not. And it takes someone who has knowledge and understanding of the guidelines to really be able to use judgment. I'm not going to just say any, brand new person can come in and just start making judgments. It doesn't work that way. But anyway, back to this. This is what we've been told we should use, and for the most part, this is the world we live in. Okay, but maybe it doesn't always apply, and this is the whole point of this talk here. What if you're doing a military base, or you're doing a school district, or a chain store? You have one client, many buildings. Okay, so what I'm suggesting here is that those ideas of the R squared greater than 0.75, or the CVRMSE less than 1/2 of the savings fraction, maybe that should not really apply if you're doing a military base, a school district, or a chain store. That's what I'm suggesting. Let's take a look. So this was my experiment. I took 235 meters. We used to, a long time ago, used to track Circuit City stores. We did M&V for an ESCO that was doing automatic controls on all their stores. I think we had 500 stores or 450 stores or something. And I just took the ones on the East Coast, 235. And I did regressions on them versus cooling degree days. Now, some of them did it versus heating, or some heating and cooling. I threw out those ones. I wanted to keep it simple. So I just did cooling degree days. And if the meters didn't have 12 bills, I threw those out too. Just keep it simple, keep it uniform. I wanted normal data, let's say. Okay, now there's also outliers, here and there, and I put them all back in. So I wanted to have bits that were less good. Less good means worse R squared and worse CVRMSE. And this is the software I use. This is actually the project. These are, all the different meters, etc. Okay, so this looks like a really good fit. I know it's kind of flat, so the R squared shouldn't be so great, but it predicts the usage pretty well. But my CVRMSE is really low. This is actually the worst meter I had. And the R squared, yeah, it's not good for a couple of reasons. One is the slope isn't so great, but the other is that I had these 2 bills. So these are estimated actual bills. Estimated bill, usually you'll see them, let's see, if you look in terms of chronological time, an estimated bill is usually low, and then the actual is usually high. And if you add them together, they're usually on the line. Okay, so what, if we're doing normal performance contracting, and this was let's say my 12-month base year period, then what I might do is I just add these 2 together and put them on the second month right here. So I have a 60-day bill, and that usually will make everything work fine. But that's really kind of an aside. Okay, so what I did in this experiment though is I left these in. So if I had estimated actuals, I left them as they were with with bad fits, because I wanted worse fits. The reason why I wanted worse fits was because my fits were really good, unfortunately. So this is, of the 235, fits, these are my R² values. I mean, yeah, some were really bad, but most of them, were really good. So I'd say probably all of these were acceptable, and then these ones were not in terms of that 0.75. Okay, but these are really good fits. Looking at the CVRMSE, the 235 meters, you can see they were also super great fits. Not that many were very bad, unfortunately. Okay, so what I did was this is just a list, just to show you kind of what I did. I had this list of 235 meters, and I had all the actual data. And what I would do is add it all up for all the meters for each month. So this would go in this right here, 17,850,000. That would be this added up for all 235 meters. And then I did the same for the baseline, or adjusted baseline. So I had two sets of data, the actual bills, and then what the fit line thought the bills would be. That would be the adjusted baseline. And then there's an error and a percent error, okay, because it's not, the fit line isn't perfect. That's what I did. And based on that, I calculated the CVRMSE. Okay, so, and I called it portfolio CVRMSE. I'm sure that people have written papers on this stuff and I haven't read them. And I wouldn't be surprised they use the same term, but maybe they did. Maybe they had a better term. Okay. So then what I did was I started removing meters from this sample. So I had 235. I did it at 200, 150, 125, 175, etc. And I started removing meters to see how does the CVRMSE change when I have different amounts of meters. That's what I did. So here you can see I have it with 1 meter. So now let's just say I removed all but one. And it was a really good fit. I mentioned my fits are really good. The first meter I had had a 0.94 R² or 2% CVRMSE. Now the portfolio CVRMSE is of course going to be the same because there's only one. If the second meter, now I add 2 meters together, and the second one didn't have that good a fit, I guess, because the average of the R² has gone down quite a bit. And the average of the CVRMSE has gone up, so it's not as good. But this is what the portfolio CVRMSE was. So that's where you add them together, and then you assume that those 2 meters are really 1 meter. What would the CVRMSE be? And I see that with 2 meters, I've reduced my CVRMSE by 10%. With 5 meters, it's down 30%. 100 meters, it's down 70%. So I had an average of 5.4, but if I did of the portfolio, it's only 1.7. And then with 235, it's still about 70. I tried this 4 times. So basically what I did was I reorganized the data. I did it by store number. So from 1 to whatever the number was. And then I did it in reverse order. So from whatever, like 1,000 back down to 1. So I had two different orders of meters that I was removing from the group. And I also did it alphabetical. Okay. So basically I had 4 different data sets. Really, it was one data set, but I just, removed meters in different orders. It was totally arbitrary. I didn't, pick the best ones. I'm not really trying to prove anything. I was just trying to figure out, what would happen. And this is graphically what it looked like. So these are the 4 trials. I don't remember which is alphabetical or which is store number, and I don't think it matters. But what you can see is, first off, it looks like it's about the same from 100 on, right? So you have 100 meters in your, let's say you're doing a military base, you have 100 meters, or you have 200 meters, it doesn't matter. It's the same. The same meaning the reduction in CVRMSE will be about the same. Okay. Right. Okay. So here I said it seems to converge around 75. I think 100 would probably be better. Here I look at it from 50 down. Okay, it's the same data. I'm just looking at it from 50 down so you can see as it goes up. So it looks like 25 on, you get most of it. 25 on, which is like 60%. reduction. So it's clear that the CVRMSE, the portfolio, is going to be a lot lower than the average CVRMSE of the individual meters. It's clear, or at least for me. That's my generalization. Did 4 different times, it happened. I think you can reduce it by 50%. That's conservative. But how many meters is required to see a 50% drop? Well, I guess it depends on your data set. But for me, I think that was just 25, right? 25 will get me a 55% drop on average. Wait, I'm sorry, a 60% drop on average. And my worst case was 55%. So 25 meters. Now, I'm sure you have plenty of school districts that have more than 25 meters. Excuse me. Okay. So that's just the same picture. All right. So why are these portfolio CVRMSEs lower? I'm sure almost all of you can guess, but I'm going to say it anyway. So CVRMSE is a measure of scatter, randomness. You know, people leave the lights on, they change the temperature set point in the zones, whatever, just little things. And the more meters you have, the more this randomness cancels out. That's the whole point. It's just the more meters you have, the more that randomness cancels out, and the usage, the aggregated portfolio usage converges to the fit line, or in other words, your scatter decreases. You have less and less scatter, and your CVRMSE goes down quite a bit. But here is a case where it does not. So what I did here, you don't need to read all this stuff, but rather than do a regression, what I did is I just said, we're just going to use an average kilowatt per day as my model. So I have data. This is the same meters. I only took 60 this time, probably starting in alphabetical order, is my guess. And I just used the average. So that means summer usage is going to be high because they do air conditioning. I mean, actual summer is higher than my average. And then winter usage, which is over here, is going to be low because they don't use air conditioning here. Okay. So what happens? Well, here I did the same type of tests, and I found that I had a reduction of CVRMSE. I guess my average was around, I don't know, 12% or something at about 20, 25 meters again. But it's only 12%. Before I was doing 50, 60% difference. So why? Why is this not good? Well, it's because all the meters were wrong. I think all of them, or probably all of them, in the same way that the summers, the fit line was low in the summer and high in the winter on all of them. And so when you do a portfolio CVRMSE, it's still going to be wrong that way. That doesn't cancel out. What's going to cancel out is the randomness. So that's what that says. Okay, so for the most part, the CVRMSE will stay high. Yeah, because in the summer, the model is always high. Great. Okay, so our conclusion, or my conclusion. The core concepts is suggesting the CVRMSE should be less than 50% of the expected savings fraction. Expect to save 20%, CVRMSE should be 10% or less. That means when you're doing regressions, if you're using option C, you're going to throw a lot of meters out. What does that mean, throwing meters out? Well, actually, that's another discussion, which I don't want to have here, but I do want to have soon. Okay, but if you're doing a portfolio, maybe you should be looking at the portfolio CVRMSE that matter. Maybe you should be looking at the portfolio CVRMSE, not the individual meters, which means you can tolerate some fits that have high CVRMSEs, or in other words, you don't have to throw out meters and you can regress all of them. That's the point. Okay, before I get to that. So, let me think about this. So what that means is you're doing a school district. You have some fits that are not good, or maybe a lot of the fits are not good, or maybe all of the fits are not good. But if you calculate a portfolio CVRMSE, you might find, oh, it's actually really good. And it is, the CVRMSE is less than half the savings fraction. Oh, there you go. Maybe that's good. Now the question is, so this is where the judgment comes in. Well, okay, that's good on a portfolio level. And really, why are you doing M&V? You want to know, do we meet our savings goal? Well, the savings goals usually are done on a school district or a military base on an aggregate level. Did we meet our goal or not on all these buildings? Maybe building A is losing a fortune, but building B is doing so great it makes up for it. So yeah, we're winning. It's working. If that's how you're seeing it, then yes, perhaps you should be using, excuse me, this portfolio CVRMSE. If, on the other hand, you want to know every building, how is it doing, and you want a good model for every building, then maybe this is less effective and maybe not the best way to go about it. Okay, here. So this is about Caltrac, the organization. I don't think they meet anymore, but they were a group of professionals, M&B specialists, and they were smart. I think a lot of them were PhDs, and they created a set of guidelines for option C methods for California utility programs. And their documentation's online, and it's good stuff, actually. They recommended that the CVRMSE of meters in a portfolio could be as high as 100%. 100%. So that's really high. The average bill is off by 100%. Doesn't mean it's high by 100%. Maybe half are high by 100 and half are low by 100. And then that will end up giving you a mean bias error of 0. Everything's right on. Yeah, that's crazy. I've never seen a CVRMSE that high. So again, let me conclude. If you're doing a portfolio, if you're looking at, your definition of portfolio is, well, I just want to look at all my projects as a portfolio. I mean, let's say you do, and I have a school district and I have 5 schools. No, let's do it different. Let's say you have a portfolio of 10 commercial or 20 commercial buildings with 20 different owners. Then this method really would not work. I mean, yes, it would work. You would see the portfolio CVRMSE is much less, but each client might want to know, well, is my building winning or losing? Are we really saving energy you promised or not? And you would have less confidence that you were, because your model was maybe really bad and you wouldn't know. So for each client, it might not be good to use this method, but on aggregate, it is good. I don't know if that makes sense. I'll try to say it one more time and then I'll be done. So the drawback of this is you will have perhaps bad models on some meters, which means your prediction of savings will be less accurate. Okay, or your estimation of savings will be less accurate. And if each of those people is a building owner, let's say an individual building owner, they really want to know if they're saving energy or not. And they don't care about the aggregate, they care about their building. Then this whole thing about having a CVRMSE of 100, it doesn't work, okay? But if they're all one owner, that's a different story. Okay, I think that's all I've got. Before I go into other webinars, let's see if I have any questions. Okay, we used to resolve the scatter by merging bills we found as the estimates caused issues until the actual bill's read. Absolutely right. That's what I mentioned. So when you get an estimated actual bill, what you do is you add them both together, and the actual comes after the estimate. It's the next month, and so you add the 2 amounts together, and you just use the second month's date. So it's a 60-day bill, and that takes care of it. And then the fit works just fine. Okay, when aggregating consumption across a portfolio that is geographically dispersed, what do you use for CDD? I don't know if I can answer that well, but I'm going to try. Okay, so that's what I did in this project, by the way. So here, let me show you the project. So, okay, this is, let's see, I'll go down here. So here is a project. I'm just looking at meters at random. I have no idea which meters these are. But this is the one I was using here. So what do? This is dispersed around the whole country. So each meter or each location will have its own weather site. So this was in Anderson, South Carolina. I don't know where Anderson is, but apparently it's near Columbia. So we used Columbia weather. So Annapolis, as you can see, we use Baltimore weather. Anniston, Alabama, we used Anniston weather. And then each building will have its own balance point. Okay, so that's that. Hey, Tyler, can you ask the questions rather than me? Because I'm really bad at that.
Yeah, have you looked at the aggregate SE and RSE of the savings without respect to the model of the CVRMSE?
I don't know. I'm sorry, I can't think on my feet to translate that sentence, so I don't.
Mark, would you raise your hand and I could mute you and we can discuss if you'd like to do that.
Hey, John.
How you doing?
All right. I actually like the way you were looking at this. This is kind of an important message that in a portfolio, we know that, you know, your errors cancel out eventually and they drift down, and generally it goes with the square of the number of samples. So, you know, a lot of what you're doing, I think, validates our intuition in this context. All I was asking is if you took the savings and the standard error from each of the sites, ignore the CVRMSEs for a moment. You know, one site saves 1,000 kilowatt hours, another site saves 10,000 kilowatt hours. We also have the standard deviations and the standard errors on each of those. Combine those uncertainties in aggregate, easy enough to do, and look at the resulting overall uncertainty of the portfolio. I mean, this is just standard utility DSM analysis that we would do. And
no, I could do that. I did not do that, but I could.
Okay,
It wouldn't be hard.
The reason I ask is that if you have two methodologies that get you to the same place, it validates or tends to support the argument for using either one of those methods. And I think, I mean, it seems that it would work. The only thing I don't know is how closely they'd be aligned.
Mm-hmm. Yeah, I don't know. I didn't do that. No, I did
Oh,
not.
just an interest, just a thought.
Well, since we have you, go ahead. We have a few minutes. Let's hear. Why don't you opine here and there? Let's hear something.
Oh, no, I think I've opined enough. I asked what I thought was a reasonably intelligent question. And I open up by saying, I like the way you have thought about this.
No, appreciate it.
That, yeah, when we're looking at 1 meter, now that, okay, we have our, you know, guidelines that we try and match, but in a portfolio context, that makes a lot more sense to say, yeah, we can live with a couple of these. It might not be as good, because in aggregate, it's going to, you know, balance out. But you've taken the effort to show that quantitatively.
Yeah. You know, the utility people, this is something they already knew, and you knew as well. They knew this stuff, and they're doing a lot of things that I think are very complicated and sometimes are unnecessary, but they're doing a lot of really interesting things that are useful to us. And I think it's really valuable to read what they're writing and learn their methods, because some of them are really useful to performance contractors. I think it's great stuff. Before I was opposed to it, and I thought this is just unnecessary complexity, and now I'm realizing, no, there's something there. There's some really neat stuff they're doing. But anyway, thank you everyone for attending. If you have questions, please email, and thanks for coming again. I'll see you next month.